Okay, ladies and gentlemen, at this point, you should have watched the Khan Academy video. You should have taken notes on the Khan Academy video. You should have done the practice problems. You should have looked at the two websites that you were supposed to outline and take notes on. And now on Monday, October 20th, you're going to get this activity. I'm not going to be in class, but it's important that you complete as much of this activity as you can. We're going to look at liquids, solids, and intermolecular forces, and we've talked about this. We've looked at liquids and solids and gases, and we've talked about temperature and how temperature impacts that. We talked about solutes, solvents, solutions, and the basic definitions of these concepts. This activity is going to have you look at intermolecular forces and what do intermolecular forces have to do with the state of matter that a substance is in. We've talked about the idea of intermolecular forces. Those are the forces in between molecules versus intramolecular forces, and this activity has you going through it a little bit in detail. All right, so as we're going through, we're going to look at the properties of liquids. All right, here they are. They're listed here. I don't think I need to read these to you. You can read them yourselves, but it's important that you read them, okay? I'm not going to go through them 1, 2, 3, 4, but you need to do it. If you don't understand these, you need to see me in tutoring. You need to email me a question. I might be able to cover it in class if it's complicated. If it's going to take too long, please see me in tutoring. If it's stuff that we've already covered, you should be able to have it in your notes already. You should have asked questions in class. And if you didn't ask questions in class as we move forward, asking questions is one of those fundamental skills of a good student. Properties of solids. When we're looking at properties of liquids, we also have to think about what are the properties of solids. And of course, we could look at properties of gas as well, but really it's liquids and solids that we're going to concern ourselves with for now. And here, of course, your standard drawing of a gas, of a liquid, and of a solid. Each of the three basic states of matter. The condensed states of matter are solids and liquids, and we call them condensed because the particles that make up the matter are close enough together. As to say, we say they're in contact with each other. Let's not even go into the discussion of the things never touch. Let's just call contact that they're relatively close to one another. Now, there's these intermolecular forces that attract, and then there's the kinetic energy of the molecules of movement that make them bounce around the room. Now, to try to explain this idea of intermolecular forces, first let's go and talk about the states of matter. When we look at the states of matter, we have things going from solid to liquid, and then other things moving from liquid to gas. In both circumstances, the particles are moving fast enough as to overcome the intermolecular forces that hold them together. Now, let me give you an example to try to explain what I mean by the kinetic energy. Remember, average kinetic energy is temperature. How the kinetic energy then can overcome these forces that hold these things together. So let's draw two rods, and let's say these rods are, they have Velcro on the side of them. So here's these two rods. These rods could be cars, or they could be people, whatever. They're moving in opposite directions, so this one's moving in this direction, and this one's moving in that direction. Let's cover the outside with some Velcro. And both the sides are going to touch. The sides that are going to touch are going to be full of Velcro. And this is going to be the hook, and this is going to be the loop. So one is the hook, and two is the loop. Meaning that they're opposite sides of the Velcro, so they're going to attract each other, right? Just like Velcro, you have to have, just like intermolecular forces, Velcro has to have opposite ends touching. If you touch two of the same side of Velcro, they won't stick, right? So it's the same thing here with intermolecular forces. The opposites attract. So if you imagine two rods moving past each other, or two people, if they're moving relatively slowly, then what do you think is going to happen if number one, which is here, comes into contact with number two as they pass by each other? I hope you said that they stuck together and they would stop. So that's what happens when materials slow down. When they're moving very slowly, the attractive forces, in this example, this is an example or an analogy, right? These two particles would stick together because of the forces that are represented by the Velcro here. Now, can you imagine for a second that these things are moving very fast, and say as fast as, I don't know, a speeding train, 60, 70, 100 miles an hour. Do you think that this Velcro, as they pass by each other and in the same way touch each other, do you think that Velcro would be able to stop these two blocks, people, cars, trains, whatever it is, from moving past each other? Do you think they would stop as if they were moving very slow? I hope your answer would be no, they wouldn't stop, because these two blocks are moving so fast that their momentum is actually greater than the frictional force that's going to hold them together, than the forces that are holding them together. This Velcro force wouldn't be strong enough to stop these trains if they're moving at a very fast rate. However, if these little trains were moving at a very slow rate, if their velocity was very low, then their momentum wouldn't be large enough to stop the Velcro, the attractive forces of the Velcro, from stopping their movement. And that's what happens in these intermolecular forces. There's the temperature, kinetic energy of the little molecules that compose everything that is. If that kinetic energy is low enough, in other words, if the temperature is low enough, then the intermolecular forces can hold them together. If the kinetic energy or temperature is too high, then they're moving too quickly, and the momentum overcomes the attractive forces that we call intermolecular forces, right? The attractive forces between molecules. And we talked about this in class. I gave you a video that you were to look at, a lecture from a professor concerning intermolecular forces, the Khan Academy lecture, the notes from the websites, etc. Now there's this thing here, these attractive forces. I don't like the way they covered this in this bullet point. The way they phrased in the bullet point, there might be a little bit of confusion. Ionic bonds, covalent bonds, metallic bonds. These are bonds between what we call intramolecular bonds. Remember the professor in the video, if you watched the video, and hopefully you did, you were supposed to, defined the difference between intramolecular bonds, the bonds that are inside these blocks, inside the molecules, versus the bonds, the attractive forces that attract the two together. This sentence is a little bit ambiguous about that, so just remember that there are these two differences, intermolecular forces, and then you have these forces inside the molecule. Two completely different animals, okay? Here we're talking about these blocks, and here these blocks are made of either covalent, ionic, or metallic bonds, and that's what makes up these blocks. The forces that hold these two together or don't hold these two together, those forces are called intermolecular forces. Let's talk about them a little bit. Here you have the types of intermolecular forces: dispersion, dipole, and hydrogen bonding. We went through that. I asked you in class as one of your exit tickets to take a look at defining them as either which one was weakest, which was the strongest, and which was the middle one. When we took a look at dispersion forces, we said that this was the weakest of the forces. Dispersion forces are these temporary dipoles, temporary. In other words, they're going to be there for just a split second, a microsecond. But as soon as they appear, as soon as these intermolecular forces appear, they impact all the other molecules in the system. So here's these two covalently, nonpolar, covalent bonded molecules. In other words, they're sharing evenly. And all of a sudden, out of nowhere, this molecule develops what we call a dispersion force, or London force. You get a partial positive, there's a delta plus, and a partial negative, there's a delta negative. you'll notice that this little sphere or electron cloud is bigger than this electron cloud. That's why this one's just partially negative. Not a full negative charge like an ionic bond, but a partial negative charge. This positive then, what does it do to the electrons over here in the molecule that's right next to it? What's going to attract the electrons? So electrons in these clouds are going to move towards it because it's partial positive. And it creates a net partial negative on this side and a partial positive on this side. And that continues throughout the entire system, right? But these forces are very, very weak. In order for this to be attracted, in order for these molecules that are nonpolar to be attracted to one another in this way, they have to have a very low kinetic energy relative to something like water or something that has a permanent dipole. So these London dispersion forces are weak forces, are the weakest of them, and so they have to have a very, very small amount relative to the other types of intermolecular forces, a very small amount of kinetic energy in order for these forces to hold them together in a liquid, and even less to hold them together as a solid. So that's London forces or dispersion forces. Now, dipole forces are these molecules that share these intramolecular bonds. Again, I reference you back to the lecture in class, the lecture and the video and the notes that you were to take. These dipole forces are permanent dipoles, so the positives and negatives align each other so that they're attracted. So the positives attract to the negative, and they all line up in a particular geometry depending on the molecules. But they all line up with the negative pointing towards the positive throughout the whole system. In this case, this would be the solid, and over here the liquid. Here you have hydrogen bonds, which are the strongest of the three. Remember, dispersion forces are the weakest. Something with a permanent dipole is a little stronger than dispersion, but weaker than hydrogen bonds. And especially strong type of bond, of course, is dipole-dipole force, but specifically when they're hydrogen bonds, they're extremely strong because these elements, fluorine, oxygen, and nitrogen, which is what defines a hydrogen bond, hydrogen has to be bonded to fluorine or bonded to oxygen or bonded to nitrogen for it to be a hydrogen bond. When those are bonded together, you're forming hydrogen bonds, not permanent dipoles, and not dispersion. And these are very strong bonds compared to the other two. Still much weaker than the covalent bonds that hold the molecule together. Now I want to point this out, and I want you to be clear on this. This is a molecule. This is a molecule. These are the forces between the molecules. These forces here hold the molecules together. And this molecule happens to be water. So this would be a liquid. In other words, there'd be a specific distance that they'd be away from each other if they're a liquid. And then a solid, if they'd be a different distance and a different geometry because of how they're oriented. But the key here is that the bonds, the attractive forces between the molecules, those are what we call intermolecular forces, and hydrogen bonding is the strongest of the three. An example of what hydrogen bonding would be responsible for is the actual shape of DNA. These two different molecules, this is one molecule here, one strand of DNA is one molecule, the other one's another strand or molecule of DNA, billions of atoms long. The strand of DNA is held together by covalent bonds, right? But the two strands are held together, and they have this particularly recognizable shape of a double helix. The reason that they have this specific shape is hydrogen bonding. It's the hydrogen bonding between these base pairs. There's either 2 or 3 hydrogen bonds for each base pair, and that's what makes this shape the way it is. So hydrogen bonds are the strongest type of intermolecular forces between different molecules, but remember, ionic and covalent bonds holding atoms together are stronger than hydrogen bonds. Don't forget that, because that's going to cost you on an exam. Please make sure that you differentiate between those two. Make notes in your notes, put them in highlight. Know that even though hydrogen bonds are the strongest intermolecular forces, they don't compare to the forces like ionic bonds, covalent bonds that hold the atoms together in a molecule. Okay, electronegativity differences, and how do we determine if a molecule is polar or nonpolar? When something is being, why is that important? Well, when we're talking about ion dipole forces, we're talking about something like water that has a dipole, a permanent dipole, right? A hydrogen bonding. When these permanent dipoles, these molecules can align themselves and surround an ion, like you see here, a positive sodium gets pulled out of its block, its ionic bonds, the ionic bonds between the sodium and the chloride. They're surrounded, and when these positives and negatives are surrounded, the bonds are weakened in between the ionic bonds between the sodium and the chloride. There's enough distance between them that it doesn't impact. They're no longer pulling towards each other as strongly. So they're able to be suspended in a liquid, in this case suspended in water. We call that dissolving. We talked about it 2 weeks ago, and we said when something goes into solution, we've been quizzed on it I think twice now. It's also on your final exam for the last quarter. And what we're talking about is the water is surrounding the ion, and the ion, in this case the salt, the sodium, and the chloride ions are going into solution. Now the question is, when do you know that you have a polar bond, and when do you know that you have whether something's polar? If it's polar, does it have hydrogen bonding or dipole forces? And if it's nonpolar, it's going to have dispersion forces, right? And if they're dispersion forces, then you know they're going to have very low. Well, we'll talk about that in a minute. They're going to have very low forces of intermolecular bonding. And if they're hydrogen bonds, have the highest of the strength intermolecular forces, and if they're dipole forces, they have the medium strength intermolecular forces. So it's important to be able to tell the difference between hydrogen bonding, dipole forces, and dispersion forces in any molecule. There's a couple things that impacts whether something is one of these three, right? How do you tell which one you have? And we're only going to deal with one very simple test that you can run on an exam, and I will expect you to be able to do this on an exam. It's not that hard, just adding and subtracting, so it really shouldn't be that difficult. But what we're talking about is we're going to compare the two atoms, and then we're going to say, well, if the differences between the two, the differences between the electronegativities, here's a periodic table with all the electronegativities of all the atoms, all the elements on the periodic table. And if the difference between any two, because remember we're talking about combining an X molecule, an X atom and a Y atom into a bond with each other, are they going to be sharing evenly? Are they going to be sharing unevenly, or is one going to take the electron? Is one going to take the electron and the other one give it up? That's the question. So what we know is this: if the electronegativity difference, if when you subtract the two electronegativities from these two atoms, this is not an element. Neither is this, right? Everybody understands that, I hope. I know that there is a Y on the periodic table. That's not what I mean by this. These are variables, okay? So let's not confuse that. In fact, let me go ahead and say sub 1, X sub 1 and Y sub 1, so we don't make a mistake in thinking that those are elements. Any two elements on the periodic table that are bonding in some way, in nonpolar, polar, or ionic, we can determine what type of bond by subtracting their two electronegativities. So if we have let's say X is fluorine and Y is hydrogen, then fluorine has an electronegativity of 4, and hydrogen has an electronegativity of 2.1. So we can take 4 of fluorine and subtract 2.1, and what we end up with is 1.9. So that's electronegativity, the delta E, that's delta E for this bond of fluorine and hydrogen, in this case example that I'm giving you. So if you have a difference in electronegativity of 1.9, then you have a polar covalent bond. 1.9 polar covalent bond. It's just that easy. Let's do another example real quick, and then we'll go ahead and let you do some exercises, and we'll move forward. Okay, so when we're dealing with when we're dealing with electronegativity, I guess you have to remember to think about electronegativity as, if you have one, here's fluorine, and if this were hydrogen or some other lower in electronegativity, fluorine is the biggest and strongest. If you see here, 4.0 is the biggest, is the largest value for electronegativity on the periodic table. So this fluorine is the strongest. When you're talking about the poor little electron in the middle, the other atom that it's making a bond with is always going to be weaker than fluorine. So if fluorine, let's say it's hydrogen, and then this is fluorine, and the difference in electronegativity is 1.9, then you're going to have a polar covalent bond. And this little electron is going to be shared unevenly, and fluorine is going to be more negative, and hydrogen is going to be more positive. So you're going to have that delta, that little delta S over here, and over here you're going to have a delta plus. So one side is going to be negative, one other side positive. This is a polar covalent bond. Now, when you're looking at if fluorine were to bond with fluorine, two fluorines, equally strong, because fluorine is 4.0, so if there are two fluorines, they have the same electronegativity. Then these two fluorines bond together, they're evenly bonded, so we call those nonpolar covalent. All right? So that's how you're going to determine whether these elements here, these molecules, are they polar or nonpolar. I'm going to give you some, there's a couple, in the video that you saw that CH4 is one of those that is the geometry of the particular, and it's just, the geometry of the molecule makes a difference for CH4 and pH3, and phosphorus and 3 hydrogens, and carbon and 3 hydrogens. But all the rest of these, you can use this procedure to decide whether something is polar or nonpolar, and it'll work. So you're talking about, is the molecule, so in other words, don't worry about D, just try to do A, B, and C for this problem set. And here you're looking, is the molecule polar or nonpolar? So how are you going to do that? You're going to do this calculation. You're going to look at the atom. You're going to compare the electronegativities. You're going to subtract them. You're going to get some value. And you're going to plug and chug into this table. Is it this, or is it this? Or is it this? So if it's polar, if the molecule is polar, it can't be a molecule that's ionically bonded. We don't. When we talk about molecules, we're talking about something that's covalently bonded. So when we're talking about molecular bonds, all right, so you're talking about molecule, is it polar or nonpolar? If the molecule is polar, then the question is, does it have HF, HO, or HN bonds? Is our hydrogens bonded to nitrogen, fluorine, or oxygen? If they are, we call them hydrogen bonds. If not, then it's a permanent dipole-dipole. If it's nonpolar, then the only intermolecular force are these London forces. So that's going to be important. Now, the last thing to consider and to remember is this ion-dipole force, this idea that those are the forces that allow molecules that are polar to dissolve other molecules that are polar, right, that are ionic in this case. So when these molecules surround the ions, they allow it to go into solution. We call that dissolving. In this exercise here, what we have to try to do is identify the bond between ionic, polar covalent, or non-polar covalent. And again, you're going to use the periodic table with electronegativities, and you're going to use the comparison numbers. You're going to subtract the electronegativities and put it into the chart, and you can decide, is it ionic, polar covalent, or non-polar? So here's water, and by now I hope you know what water is without having to calculate anything. Here's oxygen, O2, and by now it doesn't. You should know. I'm not going to tell you. You should be able to figure out that what oxygen is without doing any calculations. I'll give you a hint. O2 is oxygen is made of O2. Both of these are the same element. And then you have three molecules. You have HCN, which on your paper will show up as two grays. You can in the video you'll see the purple, the gray, and the white. The blue or purple here on paper you can consider the center atom is always carbon. You really don't need to be told the colors because you always know that the center atom has to have the most available number of bonds, and usually is carbon in this case. So carbon has 4 available bonds and therefore is at the center. So carbon's at the center, and then nitrogen's on one side and hydrogen's on the other. You have to consider now what kinds of bonds is between carbon and hydrogen and what kind of bond is between carbon and nitrogen. And something else is going on. There's an A. You're going to have to determine the kind of, you see A is pointing towards the kind of intermolecular bond, and B is pointing at the intramolecular bond. So they want to know the intramolecular bond, is it ionic, polar, covalent, or nonpolar? And the the intramolecular bond, they want to know if it's ionic, polar, covalent, or nonpolar. And the intermolecular bond, they want to know if it's London dispersion forces, dipole-dipole, or hydrogen bonding. Good luck with this. I think this is a neat activity. Here again is, another application of what we talked about before, what we've been talking about all throughout this whole thing. You'll see here this little L, and you'll see this little S. Remember, that just tells you that this is a liquid. It's a state of matter. This tells you it's a solid. It tells you the state of matter at room temperature. Remember, why is temperature important? Because temperature is defined as the average kinetic energy of a system. And so when you're measuring the temperature, you're measuring the kinetic energy of the system. The more energy it has, the more likely it's going to be one of those less condensed states of matter. So you're looking at gas or liquid. In other words, it's going to probably, the higher the temperature, the more likely it's going to be a liquid or a gas. You know that, it's common sense. But the reason is what we're talking about. The whole reason we're doing this activity is to understand why that is. So indicate the type of bonds you have here of intermolecular forces described in each of these. All right. There are no weird molecules here that where geometry is concerned, except for this one, the CO2 molecule. I'm going to go ahead and describe CO2 and tell you. Then you can go ahead and decide what it is. I'll have to tell you what kind of bond it forms. But when you're talking about CO2, it turns out that CO2 forms a straight line. So it's pretty much a linear molecule. So when you're dealing with a linear molecule and they have 2 electrons here, 2, 4, 6, 8, there's no electrons here, there's no electrons here. So these are all 8 electrons are here. Then you have 2, 4, 6. Oh, sorry about this. 2, 4, 4, 5, 6, and you need 2 more, 7, 8, and the same on this side. It turns out that carbon dioxide is non-polar. Even though when you do the math, you might come up with something surprising, you need to understand that CO2 isn't, because of its geometry, is going to turn out to be nonpolar. All right, so nonetheless, I hope that made sense. And the rest of these are following the rules that we've been discussing. And your only question is, are you dealing with ionic bonds, polar covalent bonds? Remember, if you're talking about ionic bond, you're talking about intramolecular bond. So you have to ask yourself, if it's holding the atoms together, what kind of bond is it? Is it intramolecular or is it intermolecular? If you don't know, look it up. I've explained it. You need to think your way through these questions. This is the kind of question you're going to get on exams. Are you going to be talking about holding atoms together, or are you talking about molecules? That's the question. And what kind of bonds are we asking? What kind of bonds are they asking for? And here are all the bonds that we had talked about up to this point. All right, moving on. Okay, on this page, we're looking at vaporization versus condensation versus the liquid gas equilibrium. Anytime you have a closed system, and in a closed system, it's exactly what you would think. Then there is no exchange between the environments, okay, and the system. So when you have a stopper at the end of these, what would you think it is? You'd probably think it's a closed system. So in a closed system is when enough vapor exists in the liquid above the liquid that some aqueous molecules condense back into liquid. Okay, so that what we're talking about here is that when you have any kind of substance, these molecules are always moving. So there's always some of these molecules escaping, even though it's not at 100 degrees, even though it's near 40 degrees or 50 degrees. Some molecules do escape and they end up floating around in space out here all by themselves. In a closed system, the number of gas molecules in the system out here, they'll tend to jump back out and then come back in. But they'll equal out. They'll come to some kind of equilibrium. In other words, if you had nothing, if you put it in a vacuum, the water molecules start to escape the intermolecular forces that are holding them together, the dipole forces that are holding it together, the hydrogen bonding that's holding it together. It's going to escape that liquid phase, enter gas phase, and they're going to keep going until the number of molecules gets so high inside this closed system that some of them happen to fall back into the liquid. So some are escaping, and some fall back in. And as they come back in, when the number that are coming out equal the number that are going in, there's no change, right? So think about it. If you have a molecule leaving and a molecule coming back, so for every one, if I have one molecule going back into liquid, and I have one molecule leaving the liquid, how many molecules left the liquid after you've subtracted and added? I hope your answer is none. So even though this particular molecule here did go into the liquid, that's true, and this particular molecule did leave the liquid, that's true, the change of molecules in the liquid versus those in gas phase is zero, because the ones going in equal the ones coming out. We call that an equilibrium, or something called a dynamic equilibrium. We'll talk more about that, and this is incredibly important. So you need to try your best to understand this, and we'll go over it again on Wednesday. And if you have any questions, you can email me questions as well. I'll try to answer them for you. I know I'm not going to see you until Wednesday because Tuesday we don't have class, and I'll be absent tomorrow, which is Monday. All right, so in an open system, molecules in the liquid have enough energy to escape the gas and phase and continue to escape throughout called evaporation. So true evaporation occurs in an open system. So when you see a lake or an ocean or a glass of water on your table that doesn't have a top, those molecules are just going to keep escaping until again you have some kind of equilibrium point. Till it'll keep going until it's all gone. So water, if you leave water out, after a while, all the water has gone into gas phase. That's because you have an open system, so you have a constant you have space for these molecules to keep going out. But if you have a closed system, literally closed, right, and there's something that has enclosed space, then these molecules have only this space to fill, and once they're filled, they can't go any further without having to go back into the liquid phase. All right, so I think that takes care of this particular page. If you have any, again, read it thoroughly, try to understand it, and the difference between the liquid-gas equilibrium that we're talking about here. Equilibrium is this incredibly important idea we'll be talking about throughout the rest of the year. Dynamic equilibrium is especially important. It helps with homeostasis. And remember, vaporization and condensation, two very important concepts that we've discussed, and you should really have been discussing since 8th grade. Here we'll try to do this activity, this syringe activity, as soon as I get into class on Wednesday, so we can just kind of go with it. For the sake of the activity for Wednesday, I'd like you to come up with a hypothesis. I I know this says observations, but for now in your notebooks, write down what your hypotheses are and what would you think is going to happen when you do that. If you cap off a syringe so that the syringe will not be able to allow this gas to escape. Let's go ahead and draw it. And really, as I've always said to you, when you're dealing with any kind of word problem, the best idea is to go ahead and draw it. It's a sketch. It doesn't really matter if it's a good drawing or not. What matters is that you get, well, when I say good, I mean beautiful or not. What I like to get is that you have an understanding of the problem that you're working with. So if you have this syringe, and in this syringe you have these gases, this gas, air, and you have this set here is your 0 point, and this is, let's say you have 10 milliliters of space here, and you have another 5 milliliters here that's on the other side of this wall. This wall is gonna this wall here is a dividing point. So if you can think of this wall as the dividing point, right? And as this syringe gets pulled back and forward, this space, the 10 milliliters, either is going to get bigger or smaller, and this is going to get bigger or smaller, right? You've capped off the tip, so nothing can get in or out. You've made this a closed system. So now in a closed system, as you pull in one direction, what happens as you pull in one direction? What happens if you let it go? So as you pull out, what's going to happen? Is it going to close? Is it going to push? Is it going to stay the same? Come up with a hypothesis, and when we try it in class, I'd like to see if your hypothesis matched. I want you to consider a couple things. I want you to consider the idea of air pressure. All right, it's a big one, as you'll read about here. All right, in this section of the activity. And you'll understand what a barometer is. And those of you with a new iPhone 6 Plus, you also have an atmospheric or a barometer in your phone as well. Okay, so here, explain what happened occurred. Coconut juice were just barely big enough to fit inside a straw, and you used a straw to drink the coconut juice. All right, hold on a sec. You know what? I'm going to go ahead and ask you just to go ahead and skip these two problems here, although I like the idea of this whole condensation and evaporation discussion, but these two problems I'd like you to kind of skip for right now. We'll come back to it later if we have a chance. If not, I'm sure Mr. Desipate will cover it when he covers pressure and what the standard atmospheric pressure mean. We'll probably end up going over it. I think it's important enough when we talk about how lungs work that you understand what atmospheric pressure is. So here you'll see that what you read here is what we've already discussed in class and what we discussed earlier in the video. And it's this idea of intermolecular forces versus kinetic energy, and what does it mean when a molecule escapes a liquid. And of course here we're dealing with closed systems again. Here, let's look at this question. It says, in which container, A or B, does the liquid have stronger intermolecular forces, and explain why? Based on everything we just talked about in this reading here, look at these two and tell me what you think the answer is. This is very interesting. I'd like to know. I'm going to look forward to reading and hearing from your answers to see what you think the answer is to these problems. Now, what does this have to do with boiling point or melting point? Well, just remember, the weaker the intermolecular forces, the weaker intermolecular forces, the lower the boiling point. That makes sense, because if they're weak intermolecular forces, the less energy it takes for it to be released from the hold that they have on each other. The stronger the intermolecular forces, the stronger they're held to each other, so the more energy it takes to get them to release. So normal boiling point is at 1 atmosphere. Remember air pressure, as you just saw in the other problem. If you have this container and it's open to the air, and you have a liquid, some water, and you have some of these molecules are escaping, what's going to stop them from leaving? Well, only the things that are pushing back. And what pushes back on an open glass of water, or the molecules in the ocean? The air. So it's this air pressure is the push of the atmosphere, the weight, if you will, of the atmosphere pushing down on this surface of the water. So consider that as we move forward. So we're going to look at 1 atmosphere. So you're looking at this and you're reading it, and it says that 1 atmosphere, water boils at 100 degrees Celsius for sea level, but as you go up higher, there's less pressure, so it takes less for it to move, to escape. So part of the problem here is the molecules attracting each other, and the other part of the problem is the pressure pushing down on the surface of the liquid. So we call the liquids, we can look at volatile, then we look at non-volatile. Volatile, just liquids that evaporate easily. Non-volatile are liquids that don't evaporate easily. So rubbing alcohol, as you pour it on your skin, it cools your heat, the body heat, it evaporates it really fast. It dries up really fast, and it makes your skin feel cool. That's really great. But you pour oil on your leg, that's not going anywhere anytime soon. All right, so here you go, acetone by way of nail polish remover. Think about that and look at this and read these questions. I'd like to know what your answers are here. You can't answer these. It may be a little difficult, but you might want to do a little research on the internet if you get confused, but you do have enough information to answer these 2 questions. Okay, great. So here you have these questions here. You should be able to answer based on what we discussed thus far. It shouldn't be a problem. There's 2 rules. It's like dissolves like, and that says to us that polar substances dissolve polar substances, and nonpolars dissolve nonpolar substances. So as you look at these two liquids being mixed together, dissolving each other, one dissolving the other, depending on how much you have of one. You have an octane molecule and you have carbon tetrachloride. Both are nonpolar liquids. They dissolve each other. When you mix, they mix completely, and you can't. They make a homogeneous liquid. Now, if you mix that long chain hydrocarbons we call gasoline. By the way, octane is a gasoline. That's why you can buy different kinds of octanes at your high octane fuel or low octane fuel. You can buy them at the gas station. When you're looking at gasoline, it's been added, some kind of food coloring has been added to it. You'll see that this gasoline will float on top of the water. That's because this gasoline is less dense than the water. If you look at it, they see that they're separate because the molecules themselves are longer. These water molecules kind of clump together. The water molecules hold each other because their stronger forces are holding them together. So you get this gasoline just floating on top of this water molecule. These water molecules, the layers don't mix. Oil, if you will, on water. Oil and water don't mix. You've heard that before. Miscible is 2 liquids mixing together. We call them miscible. Immiscible is when 2 liquids don't mix, right? Soluble is when a solid will dissolve into a liquid. And insoluble is when a solid won't dissolve into a liquid. Now, miscible, immiscible, soluble, insoluble, there are rarely any absolutes, okay? So things will dissolve into each other. Almost everything is soluble in everything else. It's just a matter of the degree. Is it going to be 1 molecule per year, or is it going to be a billion in a minute? It all depends on the degree of solubility or the degree of miscibility. But okay, so you have polar liquid solvent, nonpolar liquid / solvent, and you can see here from this chart what does or does not mix. Immiscible means it's not miscible, does not The two liquids will not mix. You saw the oil and water in the last slide. Miscible versus immiscible. Here, when you have, again, the same words, meaning immiscible meaning not mixing, and miscible meaning mixing. Soluble, again, means that the solid will dissolve in the liquid. Insoluble, the solid won't dissolve in the liquid. Just remember that, immiscible and soluble. And here you could go ahead and try to figure out these. Hydrophilic and hydrophilic means water loving. Hydrophobic means water hating. That comes from this this immiscibility, this like dissolves like. We came up with these terms, or somebody came up with these terms, trying to describe this in biological terms. So something is hydrophilic refers to polar molecules that are dissolved, that do dissolve in water, and something is hydrophobic or nonpolar molecules that don't dissolve in water. Extremely important when we start to talk about cells next week. Okay, for biology's sake, these solids are not, the types of solids that exist are not as important as the structure and properties of ice. That's extremely important for the sake of life on this planet. But let's go ahead and go over what some of the different crystalline solids are. All right, you have a covalent, you have ionic solids, are kind of a network of ionically charged atoms that form a very strong, high melting point substance. You could put, in fact, when they cremate people and turn every other molecule in your body into carbon dioxide or water vapor, the only thing that's left over is a bunch of salts. And that's because the salt has such a high melting point that you're not able to melt it in a crematory. And it's very interesting that the ionic solids are just very, very high, very strong bonds. When you're looking at molecular solids, you're talking about molecules, something that's made of molecules, not ions like these. These are very strongly held together. Molecular solids are not held together generally as strong as ionic bonds. They'll melt a little easier. For instance, ice is an example. Here you have molecular solid H2O. You have something that is held into a solid because of the molecules that hold it together. And then you have a metallic solid, something that actually is a great conductor. So is the ionic solid is actually not such a great conductor, but the metal is. Although, interestingly, the salt in water turns out to be a fantastic conductor. But these metallic solids are actually also have a very high melting point. As you know, metals don't take a large temperature to melt them at. So it's interesting to know that there's different kinds of solids, and those are the solids when they form a crystal. Now, water forms a crystal at 0 degrees Celsius. You've heard of snowflakes and how they each have a different geometric shape. But what's interesting here is that when water freezes, the vibrations of the water molecule the shape of the water molecule, align themselves such that there's actually literally holes in between the molecule, the ice, as it starts to form into a solid. It's the closest possible arrangement of these molecules, because of their hydrogen bonding and their shape. They form a solid that has holes in it. So it's not very dense. So if you imagine something like styrofoam, it's not very dense. If you have a large block of styrofoam, styrofoam as big as a sofa, you could probably pick it up. It's going to be very light because it's not that dense. Well, ice is the same way. Ice turns out to be less dense than water. It's not as light as styrofoam, of course, but it's less dense than the liquid form, because in the liquid form, it looks like this. They're all bunched together and moving around each other. When they form solids, they all line up like little soldiers, and the empty spaces between them allow the ice to float on liquid water. This is extremely important for life on Earth, because as the ice floats on top, the water underneath, you're able to have life living there during the coldest months of the year. And you can see these holes, these shapes that are formed because of the way ice turns into a solid. It's just very rather liquid water turns into a solid. A very special molecule. Water is a very special molecule, and one of the main reasons that life is on Earth works is because of the properties of water and how ice is less dense than its liquid form. Here you have metallic solids, ionic crystals, and amorphous materials like silica and glass. Glass tends to change shape. In fact, after a long time, some people have seen we've seen glass actually start to almost move, very kind of ooze down. Um, it's been described as something that can it doesn't have a lot of order, and also gravity keeps pulling down panes of glass, and so you get kind of waves forming in the glass over time. In metallic solids, up here you'll see that they form these kind of seas of electron, like an ocean of electrons that can move quickly from one end of the metal to the other. That's why they're such great conductors. And ionic solids, as we discussed already, are very high melting points. They're hard, they're brittle. You know them. They're called salt. The salt in your cabinet, NaCl, is one example of this kind of this family of solid materials. You actually received this chart already. You've already done this quiz, the two quizzes on this, and your final. So you should be able to draw this without any trouble. You should be able to reference your notes. But read it and try to do it, and then try to understand it in the terms of this entire packet. All right, that concludes this section on liquid, solid, gas, and intermolecular forces. And I hope that you learned something. And if you at the very least, I hope you're confused enough that our discussion and my clarification in tutoring or in class or in future videos actually helps you understand completely what we're talking about here.